Hello, everybody. Welcome back. In this lesson, we will go over the concept of limit of a function. This is a key concept behind each and every computation and each and every concept behind calculus. To understand the nature of limits, first of all, let's try to understand the difference between algebra and what we are going to do in calculus. For instance, now look at this graph. If you look at the graph, and if I ask you to give me the nature of this function at the value of a, it is very easy. All you need to do is to understand exactly the value which is lying in the domain here. It is a domain value. It is in the domain, right? You're going to get that value and you're going to substitute into the function so that you can evaluate exactly the height given by the function. So this point corresponding to the value of the function, which is computed simply by plugging the value of a into the position of x, you're going to get f of a. And the significance of this value f of a is none other than the height of this function exactly at that point. So this is going to give you a height. And you can do this computation without any issue as far as it's a value in the domain and you can just compute it. And for this particular computation, for the value of f of a or f at a, we do not need to be concerned about the behavior of the function around that particular point. For instance, whatever happens around this graph, like let's say on the left side, on the right side, whatever the mystery happening in this region, whatever mystery happening in that region, it doesn't really matter. All you're looking at would be exactly a function value evaluated at a given point. Now, let's try to understand the difference between this scenario and what we are going to see in calculus frequently. Now, if you look at this particular situation, look at this function, and there's a value um, given on the x-axis, which is named just again a. But in this case, if you look at this value, on top of that, what you see is not exactly a function value. This kind of a scenario is called a hole. So this is a hole on the graph. Let me name it on the other side for convenience. So this is a hole, and that simply means the function is not defined at a. So a is not in the domain, not in domain. And yet, now, when a is not in domain, this particular scenario, now here we consider the function g, right? It has a different name because it has a different landscape. Now, no one can talk about g at a. It is not meaningful anymore. This has no meaning. So what we did in algebra, by plugging in a function, plugging in a value to a function is no longer valid in this scenario. So what are we going to do? Are we going to throw this entire situation, I mean, entire function uh, in the garbage? Maybe not, right? Because yet this function has a lot to talk about, especially if you cannot see what's happening exactly at point A, yet you can think about what's happening around. Now think about that with a story, right? Pretend that this is just like a hiking trail. So you're going on a hike, and then now let's say when you keep up, you see something interesting. So what are we going to do? Are we going to directly jump into that? So maybe not, right? Because that's exactly what we would do in this previous scenario, like when you're moving on this path, what you're going to do is maybe like, yeah, of course, you can just jump right on top of this particular value because we know what it is. However, it's not going to make much sense if you try to do the same scenario, same thing here, because now this could be anything. It could be a pit that you have no idea what it's going to be. Once you jump in, it could be catastrophic. We have no clue what's going to happen. So, yet you can do this, right? So, when you get a grand view, like when you're expecting a grand view, perhaps you can proceed with caution, and when you proceed closer, you can get more information. You can do it from either side. When you approach from the other side, you can proceed with caution, and when you get a closer look, you can get more information. That's exactly what we are doing in calculus. So what we see under limits is not going to be a particular value evaluated out of a function exactly at a given point. Instead, it is a process to determine what kind of behavior the function is having around a given point. So let's try to prepare some kind of a notation for this. First of all, in mathematics, we love preparing notations, right? So we can have this particular observation out of a new notation, and let me just introduce that notation like this. I'm going to talk about this interesting behavior, and I'm going to call it a limit. So limit of this function, the function that we consider is g of x. So I'm going to call it g of x. Limit of function g of x when x goes to a, because we are dealing with the x-axis on right here, right? That is the x-axis. So x values are approaching from both sides, from the left or the right. They're approaching this interesting. The point of interest here is a. So while you consider the variation of your independent variable towards point A, we would be interested in looking at what's happening to the function that we are interested in talking about. So it's associated with exactly the hiking path or the trail that we are considering, right? So that is exactly the function that we are looking at. Now, if you look at this very carefully, you can see even though exactly this function is not giving us a value at A, the function values are reaching this particular height. Now, when you consider this approach, can you see along this side, the heights are approaching this particular given value L, and the same thing happening on the other side. So when x is varying or when x values are moving towards A, what's really happening on the other side of the story is the heights or the function values are approaching the value of L. Now here we have A and L. These are generic values. The, the, the idea behind it is to match it with specific numbers later with the examples. Now we make this particular scenario generic. In that way, we can map it to different scenarios. Now, let me complete this notation. What we did was, now, the limit of the function when function g of x when x goes to a equals L. So the entire story about this function, the behavior of this function at x equals a or around x equals a, is simplified into this simple mathematical statement. Now, let's try to look at another interesting scenario. Not all hikes would be smooth enough so that you can have a simple and easy path to complete. No, sometimes there could be some jumps, there could be some steep uh, ascents or descents. So now this particular scenario, if you consider this is associated with another function h of x, and you can clearly see the behavior of this function. At a, you do have a break of this function, and this particular break can be viewed as a jump. And the function is not defined. Now, think about this. In this scenario, the function could be defined just by locating one of the points. Like, let's say if I put a dot here instead of having a hole, the difference between a dot and a hole is just whether it's colored, whether it is shaded or not. Now, if you look at uh, the scenario where you have it shaded, the function could be defined. The function, the value of f h of a has a meaning if I had this dot completed. It would be the same if I did it another way, if I completed it here. That would be that particular height then, the value of h of a. But now, here in this case, we do have neither. Or it could be like at a certain instance, the function, the particular function value could be located in a completely different location with a different dot. Now, I'm not going to talk about that either. Let's say we have just this picture. What we have is this particular scenario, like where you have two different approaches, from two different sides. And in this situation, if I consider when x values are moving towards a from the left side, now if I try to match it with the corresponding portion of the graph, what we have is right this, that particular approach. Can you see it is associated with a certain height? The function values are approaching a certain height. I will name it L1 for convenience. Level 1, you can call it a level, or you can call it a limit. What gives, whatever you call it, what it gives us is the behavior of the function when you consider this particular action. When x is moving towards a, what is the limiting value? Now let me prepare a mathematical symbol for that. Limit of function h of x, don't forget. Now here I'm having a different name for the function because I'm dealing with a different landscape. Now, limit of the function h of x as x goes to a, but now I have to be specific because I'm considering only the left hand side. My x values are approaching a from the left hand side, and don't forget on real number line, when you consider x axis, left hand side simply means the negative side. So I will just do a trick. I will put a superscript here with a negative sign. Did you catch that? I'm going to put a superscript right here. So what I'm going to say is x is approaching a, but not from either side. It's approaching particularly from the left side. Let me highlight it with a different color. Maybe it's a good idea. I'll highlight it. I'll write it like x approaches a from left side. Now, that is one computation that I can look at in this scenario. And at the same time, I can look at another related computation on the other side. When x goes to uh, a from the right side, other than having the left approach, now you can see, you can guess what we are going to do. We are going to indicate it by x approaches a from the positive side. Now, if you look at these two scenarios, can you see these two mathematical sentences, these two questions, mathematical questions, have meaningful answers in this scenario? Here, the first one is settling with this particular height. It is just L1. So I'll call it L1. And then let's name this one also, give it a different name, L2, level number 2. So what's happening to the function is simply when x values are approaching a from the right side, the function values are approaching, they're sliding through this graph towards the height of L2. L2. So if somebody asks you about this kind of a situation, if you're seeing a function with a simple jump, and if you need to analyze the limits from either side, it is the simplest possible thing that you can think of. Because all you need to do is to pick the correct portion of the function when you consider either the left approach or the right approach. And based on that, you need to see where the function is approaching. So this scenario is called, this particular limit, which is associated with the left approach, is called left limit. And this one is called the right limit. And obviously, can you see there is no surprise? There's a left limit and the right limit. Now, if you try to compare this particular scenario, can you see it is not really regulated because there's a jump. That means when there's a jump, it is not nicely regulated. It's not a smooth path. So compare it with the previous example where you had almost a smooth path except for one single point where a mystery or a hole located at. In this kind of a situation, you can consider the general limiting value. This is a general limiting value. And if you break it into the left and the right approach, you can yet say limit when x approaches a from left side, in this scenario, the function g. And can you see that particular height is agreeing with exactly the right approach? The right limit x goes to a from the right hand side g of x, it's going to be the same. So both of them will agree with each other, and in that situation when they agree with each other, without a doubt one can say the general limiting value, the way to talk about the general limiting value is not to use either plus or minus superscript besides a. Here we consider minus and here we consider plus. So without considering either plus or minus, without considering the left approach or the right approach, you can simply put a right there and you can say the limiting value of function g of x when x goes to a is none other than just L. You can say that. Now, unfortunately, when you get to the next example, the second example that we've been already working with, we can see there is no agreement between these two limits. These two are not the same. If they conflict with each other. So in this kind of a scenario, we can simply say limit as x goes to a, if you consider the function of h of x, the limit of the function h of x when x goes to a. Now look at this. Look at what we did. I put a without having a plus or minus superscript. That simply means I'm not considering the left approach or the right approach. I'm not considering only the left limit or the right limit. Instead, I consider the unified limit from both ends. And in that case, since these two limiting values are far apart from each other, they're not the same, they're apart from each other, this is what we are going to say. This particular limiting value, it doesn't have a meaning. There is no value, but there is a mathematical way of saying it. Instead of having a question mark in front of a question, let's do this. Let's give an answer. In this scenario, we call it this limit does not exist. And in mathematics, we all are lazy sometimes. We would love to have some acronyms, abbreviations, so that we can just write it simply. So other than saying does not exist, usually in mathematics, we say D and E to indicate that. So when you have this kind of a limit where you have the left limit and the right limit would not agree with each other, you can simply say, right in front of it, you can write down D and E does not exist. All right, so with that, now, as a concept, how easy it could be. Now let's look at, of course, we need example with numbers. Who would like to work with just those notation symbols? That doesn't make sense. Now, yet, there's a mystery in this scenario too. I didn't give you what this function is. I didn't give you an expression for this function, but yet, let's celebrate what we have. At least we have some numbers on the x-axis and the y-axis. Now, let's look at the behavior. Let's look at this behavior, the behavior of the function at each and every point. Let's say, first of all, if I consider the first row, let me just separate these rows because each and every level is asking for a different computation. Now, in fact, at this point, my recommendation, have a quick pause. I will just put three equal signs. Now, we need to write three values in front of these three equal signs. And if you look at this very carefully, you can see all of them are associated with one single value of the domain, or one single value of the x-axis, which is 2, none other than 2, right? You consider the approach from the left side of 2, you consider the approach of the right side of 2, and you consider the approach towards 2, x goes to 2, and you're trying to see what's happening to this function in these scenarios. Now, take a moment. Based on your understanding on the previous examples, now I would like you to pause the video for a moment and write down these values as you guess. And then once you do that, unpause and continue, resume the video and see. Pause it now. All right. So now, since you already provided your answers, now you may have an idea, or like now you may have some kind of an intuition because you analyze, you look at the graph. Now think about this. When x goes to 2 from the left side, it is very easy. Let me just do it on this graph. Now, what I'm looking at on the x-axis is 2. I'm going to consider the left limit and the right limit at that point. So to do that, first of all, when x approaches 2 from the left side, what I'm really looking at is the branch of this function right here. Now, though there is a dot here, can you see it is not it is not a hole, it is completely colored, it is completely shaded. So that simply means the actual function value is defined at that point and it is located right there. And if you're concerned about that, let me tell you, in calculus, in limits, we never worry about where the function is actually defined. Whether it's a dot or a hole, we are going to treat it the same way. What really matters is this particular portion. Can you see? We're looking at the behavior of the function on the graph around that point. Now we consider the left approach. In that case, we can see the function is approaching the value of 1, the height of 1. That is the height the function is achieving. So let's do this. Let's write it down here. It's none other than just 1. And then when you consider the right approach, look at this. When x approaches from the right side, the corresponding part of the function is none other than what you see right on top of that. So consider it as the floor and the roof, right? So on top of this floor, you can see this particular roof, and what matters is which height that roof is reaching when you approach that corner of that building. All right. So what you're going to do is look at this. In that case, you can see it's getting settled with this particular height. And that's what we need. It's none other than just 2. And then when you look at the left limit and the right limit, look at this. The left limit is right here. The right limit is right there. So are they agreeing with each other? What do you mean by agreeing with each other? Are they really the same? If they're not the same, what you're going to say is it's this simple. You do not need even this kind of an equal sign. You're going to say, make it a complete mathematical statement. Limit of the function f of x when x goes to 2 does not exist. DNE. That's all. And then let's move to the next line. Let's try to see what's happening at x equals 3. Now this is easy. This is getting easy. Once you understand the concept, you will feel there is nothing actually we need to do. Just these are very intuitive. So let's try to fill these 3. When x goes to 3 from either side, now you can see it's approaching from the left, it's approaching 3. The y values are approaching 3. The height it's settled with is going to be 3. The same thing would work. Let me Just do it here. And then for the other case, it's going to be again, the right side is going to settle with 3 again. So I'm going to say 3. Now look at these two values. These two are agreeing with each other perfectly. That simply means the common limiting value at 3. In other words, when x goes to 3, the limit of the function is none other than just the value of 3. So now when you look at the limit when x goes to 5, now look at this. Here, the only difference is I put a dot right here. I emphasize the fact that the function is defined at that point. So how could it be different from all of these computations? Nothing. There is no difference. Like when you consider when x goes to 5 from the left side, the height is going to be 4. And then when x goes to 5 from the right side, what's happening on the function is exactly, it's approaching the height of 4. So what's really happening is from either end, it's settling with this particular height. So let's write down that observation right here. The left limit is 5, the right limit is 5, and the common limit is 5. Not because it's a dot here. Can you see it's a dot? The function is defined at this point compared to the previous situation where the function actually has a hole and here it has a dot. But try to understand this dot has nothing to do with calculus, or that dot has nothing to do with limit computation. It is simply, we are still following, we are sliding through this function to figure out the height the function is approaching when you consider the, the limit of the given function. So that's exactly what you need to understand. So the takeaways from this conversation, when you have a graph given, try to understand the left limit and the right limit and the behavior of those two components. If they agree with each other, you can say the common limiting value exists, and that would be equal to the common limiting value that agreeing on each side. And if not, if you do not have that luxury yet, you can talk about the left limit and the right limit. And the most important part is this entire story has nothing to do with the location of the dot or the location of the real function value. It didn't matter here, right? So let me use a different color to emphasize this. It didn't matter here. It didn't matter here. There was a dot, but that is not how we answered the question. We answered the question based on the branches of the function. And here in this case, we didn't have a dot at all, but did we worry about it? No, we looked at the function from each end and we looked at the graph from each side. And the dot was irrelevant in the conversation. So that is the main difference between calculus and algebra. In calculus, we talk about a process that governs each and every computation, and that process is called limits, the limiting process. All right, so without further ado, now let's look at the next scenario. Are we going to get all of these problems with a graph? Are we going to look at a graph and answer? Now, if that is the case, of course, wonderful. Now we know how to do that. Now, unfortunately, that's not how we're going to get it. In most cases, when you work with real world examples, you're going to build up some kind of an expression, a function, which comes with variables, and we have no clue how it's going to look, but yet we do have an expression to begin with. Now, we do not have a graph in this occasion with no graph, an example with no graph. Now, these are very important because in 90% of examples that we are going to work with, either in limits or beyond, we are not going to have a graph. So what we're going to do instead is, here, look at the left approach. Now, here we have a function. This kind of a function is called a piecewise function. because it has a couple of pieces, right? It has a couple of branches, and the branches are defined. Now if you look at this very carefully, if you do not read this mathematical symbol, first of all, try to understand the way that we define it. First of all, f of x. Function f is defined by two folds. The first one, by any chance, when x is less than or equals to, you let function f of to be 3x squared minus 1. And on the other hand, when x is greater than 2, you let the function be this linear component of 5x plus 2. Now, how does that work? I'm not going to spoil this example just by giving a graphical intuition right away, but at the end I can draw it. But for now, let's try to do this computation. First of all, let's try to do this. When x goes to 2 from left side, in other words, what we're trying to do here is to compute the left limit at 2. Don't forget, 2 is the significant value here, where you actually have these two completely different pieces combined with each other. So they may or may not agree with each other. We have no clue, but this is what we are going to do. Now let's do the computation. Let me actually bring a different color than red. Let's do the computation. Limit when x goes to 2 from left side. So when you consider the left limit, now let's try to go ahead with this piece on our hand, and let's try to see which branch corresponds to that scenario. Is it the top branch or the bottom branch? So when you consider x approaching 2 from left side, that simply means, now think about this, try to visualize. That simply means x is right here and 2 is right here. X is approaching 2 from the left side. So in this scenario, can you see the location of x is the left side? X is less than 2. So when you look at that scenario, can you see it corresponds to this branch? X is less than or 2, less than or equals 2. And now in this scenario, the definition of the function boils down to a single fold. It's not going to be confusing anymore. It's going to be just 3x squared minus 1. Only one single portion. And then with that on our hand, now we can do the computation. Now to do the computation, this is what we're going to do. Now, when you compute a limit, we should ask, graphically speaking, we know how it's going to behave. But now think about this. You know this function really well. It is a quadratic. You know the behavior of a quadratic function. It is continuous, well, smooth, right? So when x goes to 2 from either side, what's happening really at this function is none other than just it's approaching exact function value given at that point. So in other words, in this scenario, if you just plug in the value of 2 into this, you're going to get this 3 times 2 square minus 1. So now if you compute this, you can see 2 square is going to be 4, and then times 3, it's 12 minus 1, it's going to be 11 altogether. And then let's do the right limit computation. So x goes to 2 from the right hand side. And when you do this, look at this, it corresponds to the branch x approaching 2 from the right side. So that simply means this is the corresponding branch and it goes with this branch. Therefore, I'm going to name that branch in the position of f of x. Now, all I need to do in this scenario, when I consider individually again this function, f 5x plus 2, is a linear function. We know exactly a straight line. The graph of a straight line is, it's not broken at all. It's continuous. So what we're going to do is to just plug in the value right away to get the response. So the limit is going to be just plug in 2 right there. And then you're going to get 5 times 2 plus 2. So it's going to be 10 plus 2, it's going to be 12. Now, when you compare these two limiting values, can you see the left limit and the right limit? They do not agree with each other. There's a battle. So simply you can say this limit, the common limit, does not exist in this scenario. Now, I told you right at the beginning, I'm not going to spoil. I was not about to spoil this example by giving you the graphical intuition. So why don't we look at it now? If you look at this very carefully, let's have this a minor graphical representation for this function, and let's squeeze it to a corner of this entire picture, right? So what happens is, when you consider 5x plus 2, now on top of 2, when you consider x greater than 2, what you have is, now there is no equality included here, right? So that simply means you have this linear segment of the function just like this. This is the graph of y equals 5x plus 2. It goes, it skyrockets to the infinity. Maybe like it's not. Let me do this to give a better graphical intuition. I will transfer this graph. I will just draw it with more space like this. 5. So y equals 5x plus 2. That is the right branch of this function. And that is settling with the height of 12. Of course, this graph is not to a scale. I'm just trying to give you a very simple illustration to show you what kind of behavior this function is actually having. And then to the left side, what you really have is a quadratic function. So you know the behavior of a quadratic, especially when it comes to a positive leading term. So it would be almost like a U shape. So that U shape will count, and you don't need to be precise with this graph. Of course, you do not need to be uh, you do not need to do anything with this graph to answer this question, right? You did it computationally, but here I'm just giving you the graphical intuition just to conclude the idea of this problem. So if I just draw the other portion, this is how it looks. Obviously, I'm not an artist and I can see that. All right, let's do this, and it's just like that. And this portion of the function is 3x squared minus 1. Of course, this is not to a scale, but can you see the left end is settling with 11, the right end is settling with 5x plus, it is settling with 12. So this is a straight line. That is a straight line, and this is a parabola. And when you try to match these two together at that given point, of course, they do have different values, right? So they do have different behavior, and therefore they end up getting different values. Therefore, there is no connection, or there is no continuity in this function. And we will see these kind of examples more in detail when you get to a later, very straightforward section called continuity of a function. So in that scenario, we will revisit the left limit and the right limit, and it's just about like combining these two pieces together to see the continuity of function. You can already guess that scenario. So this is exactly a supplemental question. Can you see, is this function f, the given function f, is it continuous at x equals 2? Think about it, point to ponder. So with that, actually, we come to a conclusion of this first lesson. And what we did here is to build the concept of limit. Try to understand it graphically and intuitively. Of course, we need to do computations later, but try to understand it is very important to understand the concept to see what we're dealing with and to be able to have good grip on the computations. First, you need to understand you what kind of concept it is, right? So that's exactly the purpose of this particular lesson, to define limits, to start limits intuitively, and to work with graphical examples, and to be able to work with um, piecewise functions just as you're given in this particular example. So with this, we conclude the first part of limits, and we will meet on the next video lecture, which will be about limit computations.